In this phone, there are nearly 100 million transistors. In this computer, there's over 1 billion. The transistor is in virtually every electronic device we use. TVs, radios, Tamagotchis.
But how does it work? Well, the basic principle is actually incredibly simple. It works just like this switch. So it controls the flow of electric current. It can be off, so you could call that the 0 state, or it could be on, the 1 state. And this is how all of our information is now stored and processed in zeros and ones, little bits of electric current. But unlike this switch, a transistor doesn't have any moving parts, and it also doesn't require a human controller. Furthermore, it can be switched on and off much more quickly than I can flick this switch. And finally, and most importantly, it is incredibly tiny. Well, this is all thanks to the miracle of semiconductors. Or rather, I should say the science of semiconductors. Pure silicon is a semiconductor, which means it conducts electric current better than insulators, but not as well as metals. And this is because an atom of silicon has 4 electrons in its outermost or valence shell. And this allows it to form bonds with its 4 nearest neighbors.
Howdy-ho there.
What's up? So it forms a tetrahedral crystal. But since all these electrons are stuck in bonds, few ever get enough energy to escape their bonds and travel through the lattice. So having a small number of mobile charges is what makes silicon a semiconductor. Now this wouldn't be all that useful without a semiconductor's secret weapon, doping. You've probably heard of doping. It's when you inject a foreign substance in order to improve performance. Yeah, it's actually just like that, except on the atomic level. There are 2 types of doping, called N-type and P-type. To make N-type semiconductor, you take pure silicon and inject a small amount of an element with 5 valence electrons, like phosphorus. This is useful because phosphorus is similar enough to silicon that it can fit into the lattice, but it brings with it an extra electron. So this means now the semiconductor has more mobile charges, and so it conducts current better. In P-type doping, an element with only 3 valence electrons is added to the lattice, like boron. Now this creates a hole, a place where there should be an electron, but there isn't. But this still increases the conductivity of the semiconductor because electrons can move into it. Now, although it's the electrons that are moving, we like to talk about the holes moving around because there's far fewer of them. Now, since the hole is the lack of an electron, it actually acts as a positive charge. And this is why P-type semiconductor is actually called P-type. The P stands for positive. It's positive charges, these holes, which are moving and conducting the current. Now, it's a common misconception that N-type semiconductors are negatively charged and P-type semiconductors are positively charged. That's not true. They are both neutral because they have the same number of electrons and protons inside them. The N and the P actually just refer to the sign of charge that can move within them. So in N-type, it's negative electrons which can move, and in P-type, it's a positive hole that moves. But they're both neutral. A transistor is made with both N-type and P-type semiconductors. A common configuration has N on the ends with P in the middle.
Just like a switch, a transistor has an electrical contact at each end, and these are called the source and the drain. But instead of a mechanical switch, there is a third electrical contact called the gate, which is insulated from the semiconductor by an oxide layer.
When a transistor is made, the N and P types don't keep to themselves. Electrons actually diffuse from the N type, where there are more of them, into the P type to fill the holes. This creates something called the depletion layer. What's been depleted? Charges that can move. There are no more free electrons in the N type. Why? Because they've filled the holes in the P type. Now this makes the P-type negative thanks to the added electrons. And this is important because the P-type will now repel any electrons that try to come across from the N-type. So the depletion layer actually acts as a barrier, preventing the flow of electric current through the transistor. So right now the transistor is off. It's like an open switch. It's in the 0 state. To turn it on, you have to apply a small positive voltage to the gate. This attracts the electrons over and overcomes that repulsion from the depletion layer. It actually shrinks the depletion layer so that electrons can move through and form a conducting channel. So the transistor is now on. It's in the 1 state. This is remarkable. Because just by exploiting the properties of a crystal, we've been able to create a switch that doesn't have any moving parts, that can be turned on and off very quickly just with a voltage. And most importantly, it can be made tiny. Transistors today are only about 22 nanometers wide, which means they're only about 50 atoms across. But to keep up with Moore's law, they're going to have to keep getting smaller. Moore's law states that every 2 years, the number of transistors on a chip should double. And there is a limit. As those terminals get closer and closer together, quantum effects become important, and electrons can actually tunnel from one side to the other. So you may not be able to make a barrier high enough to stop them from flowing. Now, this will be a real problem for the future of transistors, but we'll probably only face that another 10 years down the track. So until then, transistors, the way we know them, are going to keep getting better.
Once you have, let's say, 300 of those qubits, then you have like 2 to the 300 classical bits, which is as many particles as there are in the universe.
It's Friday morning. I was supposed to do this lecture yesterday, didn't get it all the way done. So we ended up here, slide 47 on chapter 34. I did find some other resources. I had some questions myself. How does the amorphous silicon participate in the photoelectric effect? Well, it really doesn't. Down at that level, they call it the photovoltaic effect. And you can look that up on the internet. It basically works like a solar panel works. So, and I did include a video about semiconductor technology that covers, it rehashes P-type and N-type diodes. Diode bridges are also called rectifier bridges, transistors, and then finally talks about solar panel technology. So from solar panel technology, you should understand how the amorphous silicone wafer is absorbing the light from the cesium iodide layer in the indirect DR. Basically, the amorphous silicone layer is acting like a solar panel. If you push light at a solar panel, it starts conducting electricity. This is called the photovoltaic effect. Very similar to what you see in the photoelectric effect, except the energy threshold is lower for the photovoltaic effect. Will the photovoltaic effect be on your registry exam? No, it will not, so you can skip that part. Just understand that the way that silicone reacts to light is very similar to a photoelectric effect event. But a physicist would correct you and say, no, it's a photovoltaic event, not a photoelectric event. So anyway, so now we're going to talk about the spatial resolution of the digital systems, all three technologies, CR, DR, indirect and direct. We're going to find that direct DR has the highest spatial resolution typically, not always. All of it is dependent upon, in DR technology, the size of the DXL, and in CR technology, the diameter of the laser. So I'll get into the explanations of those. Here we go. All right. So, and then there's the Nyquist frequency. What the heck is the Nyquist frequency? Well, Mr. Nyquist was the first one to digitize audio signals from analog in early work for Bell Laboratories in the 1900s. I think it was, don't quote me on this, but I think it was 1930 or 1940. He was working on digitizing audio signals, analog audio signals, and converting them to digital signals. And what he found was an interesting principle. So for any wave, crest and trough, you have to sample that wave. One wave has to be sampled at least twice. And that means the sampling frequency. So if you're trying to duplicate, let's say, a 5 hertz sound wave, okay, you need a sampling frequency of 10 hertz. That is, you need to sample every wave twice. Okay? Otherwise, you're going to get a interference pattern in your sampling as you're converting the analog. Because when you convert from analog to digital, you don't use all of the analog signal. You take finite measurements at points on the timeline, and then you estimate the analog signal. Well, what Nyquist figured out is if you don't take enough measurements proportional to the cycle of the native wave of whatever it is you're trying to reproduce or convert from analog to digital, if you don't take enough sampling measurements frequently enough, then you get what's called a fold-over bias or an aliasing bias. Okay? Now, people who have played video games all the way back to the 80s, they're quite familiar with aliasing bias. And then if you've also, you can see aliasing bias if you take a cell phone picture of an LCD monitor. You will see those crazy little wave stripes artifacts roll up. Some people call it the corduroy sign. If you are not near a digital monitor right now, you can take a cell phone picture of the side of a brick building, because the brick has a native frequency too. And depending upon if you just keep zooming in and out, eventually you'll get this aliasing fold-over bias, and that's a sampling frequency error based on the Nyquist frequency. So Nyquist says, for repeating patterns, frequencies, your measurement frequency has to be double the native frequency, okay? So we know that from the previous chapter, we know that X-ray images can be expressed as a summation of various frequencies, okay? So we're talking about the smallest frequency, the very high frequency ones. So that would refer to the tiniest objects, and this is where Nyquist makes the most sense, is eventually an object is going to get so tiny that its frequency is going to be so high that you are not sampling it enough. And when you don't sample it enough, then you can't accurately make a representation of it in digital form. That's what Nyquist is really saying. Okay? On the registry exam, they're going to want you to know sampling frequency must be at least twice the native frequency of the object you're trying to represent. Excuse me. All right, so what is the smallest frequency? Well, wouldn't that be one pixel was a crest and another pixel was a trough? Kind of like a line pair, and we'll get into that in QA/QC. But yeah, a line pair, which measures spatial resolution, represents the smallest frequency as well, because one of the pixels is the black line, and one of the pixels is the white line. Okay, and so your Nyquist frequency or your sampling frequency is connected to the spatial resolution measurement, line pairs per millimeter, because a line pair of 1 pixel across for the black line, 1 pixel across for the white line, that is the smallest object you can represent. Because how do we spot objects on X-ray? Yes, we don't see objects, we see edges of objects. And so how do you represent an edge? Well, you need at least 2 pixels, different colors. That's how we represent an edge. And so therefore, the Nyquist frequency is tethered to the pixel size. If the pixel sizes are smaller, then that is a higher spatial resolution, because the Nyquist threshold is satisfied. You can represent tinier waves or tinier edges with smaller pixels. Okay, maybe go back and listen to this slide one more time, but hopefully we'll keep pursuing this. Okay. Now, pixel, del, and dot pitch, or pixel size, all those are synonyms. Why do we have 4 different names for those? We have 4 different names for those because all of those names are proprietary. Someone has trademarked pixel size, and our ridiculous U.S. government has allowed that trademark. Those are 2 just common use words. The word pixel is in common language. It doesn't belong to anybody. The word size is in common language. It doesn't belong to anybody. But now if you say both of those together, oh, that's a trademarked term. Ridiculous. So we have to say pixel size, pixel pitch, dexel size, dexel pitch, or dot pitch. All of them mean the size of the pixel. Okay. Technically, the pixel pitch is the distance from the center of one square to the center of the adjacent square, like the red indicator on the left picture is indicating. Okay. But even if you're not a student of geometry and you have 2 squares that share an adjacent side and both of those squares are the same size, then the length of one of the sides of the square is equal to the distance between the centers of both squares. That is a elementary geometry proof. You half a piece of paper and drawing things out and labeling the side of the square A and the distance between the center and the edge of the square B, and then trying to express A in terms of B, and you get, very simply, you get A equals 2B. Because B is half of us. That's what we mean by the center. start at a side and then stop in the middle of the shape. And so necessarily B is half of a side length. So 2 half side lengths equals a whole side length. And that's what you have when you're going from the center of one to the center of the other. It's just a different way of saying the same thing. So pixel size always refers to the length of a side of the pixel. Pixels are typically square. For the purposes of the X-ray curriculum, pixels are square. Okay? Yes, some monitors have hexagon weave matrices for pixels. And so it's more appropriate to talk about pixel pitch than it is pixel size. But for squares, those terms mean the same thing. But you have to know both of those terms. Pixel size and pixel pitch are the same. It means the same thing for square pixels of uniform sides. Okay? So the Dexel pitch also includes the space for the address driver wires, that is the control or the gate lines, but then also the data lines. Remember, we covered that in the first part of the chapter. The control or gate lines run horizontally in between the DELs or the Dexels, and the data dump lines run vertically in between the DELs or the Dexels. All right, spatial frequency is given by the formula 1/2 times the pixel size. Okay, and a pixel is measured in millimeters, and we need 2 pixels to represent the smallest line pair, so that's where the 2 comes from. So the formula is easily derived. Spatial frequency expressed in line pairs per millimeter is 1/2 times the pixel size. And sometimes they try to get tricky, and in those questions they say smallest object resolved. Well, the smallest object you can represent is the size of a pixel. Okay, we talked about that. If you have a tumor smaller than the pixel, then the color, the attenuation color of the tumor and the attenuation color of the healthy tissue are going to be averaged. And so you lose the ability to express the tumor. But if the tumor is at least as big as 1 pixel or bigger, then there's no problem representing the difference in attenuation. Okay? Because the next pixel over can be the different color. Okay? But this is, we cannot represent 2 colors on a single pixel. Every pixel only reports at 1 color value. Okay? So eventually we get to the bottom of the pixel size, and if the object the pathology we're trying to display is smaller than the pixel size, then it's going to be invisible to our X-ray system. Okay? It's kind of like electrons. We know they exist. We can see their effects. Can you see an electron? Why can you not see an electron? Because your eyeballs use rods and cones to see what? Objects that are bigger than light photons. But we can't see protons, we can't see electrons, we can't see neutrons, not with the naked eye. The reason is because atoms are so small that we can't accurately, the native resolution of our eyeballs doesn't let us see things that small. We can see macro-sized objects, billions and billions of atoms, but we can't see individual atoms. In the same way, if we think of our image receptor as an electronic eye, it also has a lower limit to how small an object it can see. That's really what we're talking about. So we have this shows you how spatial frequency is indeed expressed as line pairs per millimeter, because pixel pitch or Dexel pitch both are 0.1 millimeter, And so if you color one in white and the other one black, and then do the same again, white, then black, alternating white, black, white, black, you are going to, it's going to appear to you, depending upon which color you're focusing on, that you have 5 black stripes in 1 millimeter and 5 white stripes in 1 millimeter. And so therefore you have 5 line pairs per millimeter. Now the smallest object is a line, but we express it as line pairs, okay? So because we want contrast, we do this because we want contrast to affect the way we do this measure, and it will. That's why we can see the line pairs, because we can recognize the difference between bright white and black. And so the reason the black one shows up is because it's surrounded by white, and the reason the white ones show up is because they're surrounded by black. In other words, we have a high contrast here, okay? But that contrast will start to break down as a native frequency that is way too high, or that is the pixel frequency in a horizontal vector or a vertical vector across our image receptor does not match the frequency of the object. It's too low to accurately record the frequency of the object. So, spatial frequency formula practice. What's the spatial frequency for an imaging system with a Dexel pitch of, so Dexel size or pixel size of 0.04 millimeter? Okay, so it's line pairs per millimeter that is the final answer. And so using millimeters, we don't have to do a metric conversion. Sometimes they will use micrometers in these questions, so you got to watch out for those. Do a metric conversion back to millimeters first. I think this is actually either 4 or 40 micrometers, but I don't have the conversion table in front of me right now, so that's a guess. Okay, so remember we said spatial frequency is 1 over 2 times the pixel size. Okay, so the pixel size is 0.04, 2 times that is 0.08. And then just hit your 1 over X button and you come up with 12.5 line pairs per millimeter. What does the half mean? Well, that means there was an extra white column, no paired black to it. Okay, so there are 12 pairs, white, black, white, black, white, black, you get the idea. And then the half line pair would be just either a single white stripe or a single black stripe, also in that distance. At what distance? 1 millimeter. Okay. So, I know Mr. Shepard told you that sharpness of recorded detail, which is still true, is related to some geometric factors, notably OID, SID, and focal spot size. And that's all true. That will encode a certain spatial resolution into the image. But ultimately, the pixels are far smaller than the focal spot size. The pixels are smaller than any magnification or minification ratio. And that, so it's better to say that all the stuff Mr. Shepard taught you about magnification formula and focal spot size and edge blur and things of that nature, those influence the remnant beam, but they are not in the final control of the spatial resolution of the displayed image. What is in final control? Ultimately, it is the size of the detector elements, or pixels, and by pixels I mean laser diameters and CR technology. It's the size of the sampling. What's the smallest component? You're trying to catch the image with the entire image receptor, but a sample of that image is what lands on one detector element. That's sampling. It's sampling in a specific location, but it is a sample of the image, okay? Each one of the dells represents a sample of the image. In CR, each laser strike represents the sampling of the image. Okay? And so these how big is the sampling area ultimately determines sharpness. Okay? The smaller the pixel, the better the sharpness. Spatial resolution improves with smaller pixels. Now, what was this we said in the first section that is affected in a bad way with smaller pixels? Yes, your fill factor, your capacitors and your thin film transistors are already as small as they could be, and so making the pixels smaller typically sacrifices the fill factor, and then that creates other problems. Pixel size formula is field of view divided by matrix. Okay, but ultimately pixel size is actual physical detector element size. Okay, and so they do want you to know this formula. You got a matrix size of 1024, but your field of view is 305 millimeters. That is the length of one side of the collimated field. Now, a better formula would be to use an area for field of view and to use an area for, instead of just side length. So when we say a matrix size of 1024, that means the side length of the matrix is 1024 pixels long, okay, on your imaging plate. 30.5 millimeters would be, 305 millimeters would be 30.5 centimeters, and that's going to be about 12 inches long, okay? So 1,024 pixels evenly spread over 12 inches, okay? And so your pixel size becomes that ratio. It looks like they worked it out to 0.3 millimeter pixel size, right? Yeah, not going to do the English conversion for that. You guys can wrap your head around 1/10 of 3 millimeters. So, because you can see a millimeter on a proper metric ruler, and you say, okay, divide that tiny little space into 10, and then count 3 of those over. Okay. Now, if you have a friend who's an engineer, he's going to have a more sensitive instrument for measuring tiny distances, and he might actually be able to show you what 0.3 of a millimeter look like. We can only estimate what a 0.5 millimeter looks like on a conventional ruler because the graduations stop at a whole millimeter. So we can figure out when it's oh yeah, that's halfway across. So we got to get pretty good ballpark on that. But to subdivide it further and say, is that 0.45 or is that 0.52? That's kind of tough. You see? So we know you can always estimate the next half of the listed measurement on any graduated device. So like a ruler that goes to millimeters, you can guess to the nearest 0.5 millimeter. All right, so field of view can be defined in several different contexts. Physical size of a display monitor or the image receptor, size of a collimated field, or level of magnification applied at the display monitor. Okay. Only in Mr. Carroll's mind can you define field of view 3 ways. On the registry, it's definition number 2. Field of view represents the collimated field. Now, according to him, a software magnification that allows you to zoom or magnify affects the field of view. Yes and no. It affects the displayed field of view. However, the natural field of view for the original image is always the same until the image is destroyed. Now you can manipulate it by magnifying and zooming it, but the original image had all the anatomy, and that's the field of view for the study. It's the size of the collimated field. Zooming up doesn't change the size of the collimated field at the time of exposure if you zoom up in post-processing. In fact, zoom back down, voila, there's the rest of your picture that was missing just a second ago. Or hit the reset button if you can't zoom back down right, which is kind of tricky. Okay. Pixel size, can we apply the soft pixel size formula? Well, it depends on if the field of view is a fixed field of view or a changing field of view. Okay, and so the best way to improve spatial resolution would be to add to the matrix size and reduce your field of views. Okay. Several different types of matrices, just like there's several different types of detector elements or pixels or whatever. So we've got a lot of matrices. The hardware matrix is the physical detector elements on the DR plate. Light image matrix, that is the bolus of blue light photons heading into the photomultiplier tube and then transitioning to the analog digital converter. Okay. Hardware matrix. The hardware matrix is the displayed digital image, and it does display in pixels. Okay. And then the light matrix of the displayed image itself. So if you turn off all the lights and then you get a fog machine like you have at Halloween, you can actually see the LCD broadcasting the light of the displayed image out into the air, and technically that's the light matrix. I've never heard of the light matrix before just now. All right, I'm going to pause a little bit. I'm getting kind of cockmouth. Give me just a second. So you might have figured out that the Dexel size basically is the fixed threshold for spatial resolution. You can't have a soft pixel size formula, field of view versus matrix, that comes out to a spatial resolution or a pixel size less than the size of a DEL. All right, so the detector element size ultimately limits the pixel size. Okay, so it says right there in the last bullet point, the soft pixel size formula, field of view divided by matrix size, does not apply because the DEL ultimately controls what the size of a pixel is. You can't have half a DEL become a pixel. So if the pixel size calculated by the soft formula is less than the size of the DEL, then it's the DEL size that becomes the pixel size. Okay? So fixed matrix systems. This is what we have in the Kodak Carestream CR. Okay? In a fixed matrix system, Kodak Carestream has a 525 by 525 matrix or something like that. Okay? No, 512 by 512. Okay? That means the 14 by 17 plate has a 512 by 512 matrix, but the 10 by 12 plate also has a 512 by 512 matrix. What that means is when you use 10 by 12 plates on Kodak CR, you're actually improving spatial resolution because it's the same size matrix applied to a smaller physical area. And so the pixel sizes get smaller, and you can see this side by side right here. The left is the 14 by 17, and the right is the 10 by 12. We have the same matrix size applied to two different sized physical spaces. Okay, you can say that the matrix size has to be, the matrix has to get bigger to cover the entire 14 by 17 cassette, so each individual pixel has to grow and expand. Or you can say that we shrink the physical size of the matrix to apply it to the 10 by 12 cassette, and therefore each pixel in the matrix also shrinks. You're basically saying same thing, as long as you understand the concept. Okay? This is usually only CR plates that have a fixed matrix system. Now the DR plates have fixed matrix system too, but the DR plates don't have different cassette sizes, so you don't see this phenomenon. CR plates, the 10 by 12s, the smaller cassettes are usually higher resolution than the bigger cassettes. Okay, and you can totally confirm that with a line pair test tool. I have one at the school if you want to shoot some X-rays on the CR cassettes and the 10 by 12s and the 14 by 17s. You should see that there's a loss of resolution on the 14 by 17s. We might add that to our lab that we've got at the end of this. Okay. So smaller IR, shorter rows, narrower columns, therefore pixel sizes are smaller. It's basically saying what I just explained. So moving on. Okay. So consistent spatial resolutions, how are they maintained? Well, the sampling is still the diameter of the laser. So as long as the diameter of the laser is smaller than both of these pixels, it says fixed sampling. So you make the pixel size uniform, and then the matrix grows for a larger image receptor. You see? And so both those pixel sizes are the same, but now the matrix sizes are not the same for a fixed sampling system. That would actually be an improvement. So you get a consistent spatial resolution out of a fixed sampling system. When you have a fixed matrix system, the spatial resolution changes with image receptor size. Okay. The pixel size formula does apply to a fixed matrix system. So the first iteration, the pixel size is the ratio of field of view to matrix size. But in a fixed sampling system, the pixel size is set and the matrix actually grows to accommodate an increasing field of view. It's not correct to say that the ratio doesn't apply anymore. It's more correct to say the pixel size is fixed. So the left side of the equation is constant, and therefore if field of view increases, matrix size has to increase so that the ratio is maintained. That's the more correct way to say the second bullet point. All right. So spatial resolution for CR units may be variable. Kodak Carestream, it is. The 10 by 12 cassettes have a higher spatial resolution than the 14 by 17 cassettes. Okay. Our efficiency, this is our DQE. Okay. Our storage phosphor plates. The front part of the plate, the point toward the X-ray tube part of the plate, or the cassette, if you will, has to be radiolucent. We want as much of the remnant beam to pass through without absorption as possible. That's why carbon fiber is such a good material for the front. Okay. 3 types of efficiency apply to image phosphors. Absorption efficiency. Okay, that's photoelectric conversion efficiency, or photoelectric absorption or photovoltaic effect in some situations, like I covered earlier, like on the first slide. Conversion efficiency, if you're converting to light and then light to electrons in a second step, how efficient is the second step? And then emission efficiency refers to either emission of light or emission of electrons. So how do we increase absorption efficiency? Let's use a thicker phosphor. What could go wrong? Well, you're going to get more light spread. And so what's going to happen to your spatial resolution when you use a thicker phosphor? You are going to increase your DQE. You're going to catch more of those X-rays because the active layer is thicker. And so the highly penetrating photons have a chance to get caught too, because we got to go through, linear energy transfer. It's not just for flesh. Okay. Use of materials with a higher atomic number. Obviously, that's how we trigger the absorption of X-rays. Photoelectric effect is proportional to the Z number of the target atom. That will answer at least 3 questions on your registry, so make sure you remember that. I said photoelectric probability is proportional to the Z number of the target atom. Okay? Proper matching of the K-edge to X-ray beam energies. Now, what the hell is the K-edge? Well, it's the K-shell binding energy for the target material. If the incoming photons and the binding energy of the target atom are nearly the same, or they approach a close proximity, well then photoelectric absorption takes off like a rocket. So, and I think I've got a K-edge phenomenon graph at the end of this PowerPoint to show you. So, or hopefully in the upcoming slides here. And then conversion efficiency, percentage of the X-ray that is converted into light rather than infrared or heat, because we know that it's light that carries the data to the next step, whether that be the light guide, acrylic, or fiber optics going up into the photomultiplier tube, or whether that be light heading down into amorphous silicone to create a photovoltaic effect. Okay. Emission efficiency, ability of the light produced to escape the phosphor layer and reach the photomultiplier tube. This is for CR plates. Okay. Remember, DR doesn't have a photomultiplier tube. Sorry guys, had a little cough that I had to take care of there. All right, emission efficiency. How do you, if you're a light photon, can you get reabsorbed by the phosphor layer? And the short answer is yes. Okay. Light is emitted isotropically because all electromagnetic radiation, when it's created, is isotropic source. Even the laser, we did mention that, the laser technically is isotropic source, but then you've created that light spreading in all directions in a cylindrical mirror, which turn inward inside a cylinder, and you only have one aperture for the exit point. And so lasers seem to violate the isotropic rule of X-ray, or I'm sorry, electromagnetic radiation spawning in all directions and traveling in all directions, but it doesn't. Inside the mirror resonance chamber, the light is traveling in all directions. Okay, it's just being totally reflected back into the chamber. So for the case of cesium iodide, you do get these needle-shaped phosphors, and it acts as a fiber optic, and so the photons can only travel up and down. And that's why cesium iodide is a better, between the two phosphors that are commonly used, cesium iodide is a better one because you get about 50% of the light energy heads downward toward the amorphous silicon. Okay? Emissions efficiency, light emitted backward can be captured using a reflective layer. This is in a CR plate. And so when you make the blue light from releasing the electron trap, the blue light can head up toward the light guide and be captured, but the blue light could also dive deeper into the detector plate, and hopefully that's where it'll hit the chrome reflective layer, and then it'll ricochet and bounce back up. Now you do lose a little spatial resolution with that maneuver, especially with a thicker phosphor layer, but you do improve the emission efficiency of the CR with the reflective layer. Okay. All right, and now the K-edge effect. So here's lanthanum. What the hell is lanthanum? Well, it's just an element, and it has a K-shell binding energy of 39 kiloelectron volts. You can look it up on the internet if you like. And so when you are shooting photons at it, the photoelectric effect sharply increases when you approach about 40 keV or 40 kVp if you prefer. Okay? So this sharp increase in the probability of the photoelectric absorption of lanthanum and this is conditional of all elements. Every element has a K-edge effect, where the energy of the binding energy matches up nearly perfectly with the photon energy. You always get this spike in the probability of absorption called the K-edge. So, yeah, it kind of looks like a rip saw blade or chainsaw blade. That's always the K-edge effect. It's an increase in absorption right at that specific energy level. Okay, and so you should pick your active layer materials based on their K-edge. Okay, you typically want, where are most photon energies for the diagnostic X-ray beam? Usually they're between about 40 keV all the way up to 60 keV. Remember, we're talking about average kilovoltage or average energy. Remember the beam spectrum curve? The top of the Bremsstrahlung hump is usually 1/3 of the voltage. So somewhere in the high 30s or a high 20s, low 30s is your average energy. So lanthanum would actually be a pretty good image receptor material. Okay. Photoelectric effect by the conservation of energy cannot take place unless the energy of the photon is higher than the binding energy of the electron it's trying to release. Okay, you have to pay for the release of the electron. It's kind of like paying bail. Okay, if the bail is set at $200 and you show up with $185, I'm sorry, your buddy's not getting out of jail. Try again. Okay, so it's the same thing. The electron is essentially trapped in the orbit, and the photon has to show up with enough bail money, enough energy to spring the electron. Okay, that's a nice parable. I like that one. I'm going to build that into I'm going to make illustrations or steal illustrations and make a little story about how the K-edge effect is like paying bail money. I'll be doing that for next year's class. So. X-ray beam spectrum curve reveals that the average energy is about 1/3 keV. We learned that back in chapter 10 in physics. Okay, and so that means roughly, so at the low end of the diagnostic range, what is that, like 50, 52? So 50 divided by 3 is it's less than 25 because that's 50 divided by 2. But it's greater than 10 because that's 50 divided by 5. So partway between 2 and 5, but closer to divide by 2, yeah, 17. Okay, so that's where the number 17 came from. Oh, look, I have my calculator right here. Let me see. The low end of techniques that we set is 50 kV. All right, so 50 divided by 3, 16.6. Lo and behold, wow. Okay, and then what's the high end of our, don't we want to go to 120 for our chest X-ray? 120 kVp divided by 3, 40. See, that's where you got the range from. So K-edge for lanthanum is at 39, so it could be, used for conventional screens. So in screen film technology, we totally use lanthanum. Okay. Okay, so if we set a peak kilovoltage at 76, lanthanum, we wouldn't be taking advantage of, we'd be taking slight advantage of lanthanum's effect. And then bromine would be at the bottom edge of the most probable number of photons. Okay. Use of phosphor elements with lower atomic numbers can sometimes better match the K-edge to the average X-ray energies, thus improving absorption efficiency. And so we want higher atomic numbers, but we don't want them so ridiculously high that the K-shell binding energy is outside of the most probable X-ray energy. You see? So we want to match the K-edge to the middle of the Bremsstrahlung curve. And that's how we choose what materials we use to build our CR and DR, indirect DR cassettes out of. Okay? So conversion and emissions efficiency are also issues for indirect DR systems, because we're also dealing with light spread, we're also dealing with phosphors. So how good is the phosphor at catching the photons? Does that readily trigger a light emission? Does the light spread in all directions? Does the light make it out of the phosphor? So everything that applied to the photostimulable phosphor also applies to the indirect phosphor layer, which is usually cesium iodide or gadolinium oxysulfide. But in a direct conversion system, the layers of the dexels must be kept very thin, so they're dependent upon higher atomic numbers to increase the probability of photoelectric absorption. So we need to look up, I told you we needed to look up what the K-shell binding energy was for. Let me pause and see. Yeah, K-shell binding energy of selenium is 12.6 kilo electron volts. So we need lots of 12.6 or just a little bit higher than 12.6, and then we'll get a good K-edge effect. So looks like amorphous selenium is perfectly K-edge centered to our most probable Bremsstrahlung X-rays, or Bremsstrahlung X-rays of the most common energies. Okay? So the indirect conversion system, low energy light photons by the active matrix from the cesium iodide phosphor is much higher than the absorption of high energy X-rays of a direct conversion system. So this is where I was saying photon counting is just a marketing gimmick. The detective quantum efficiency of the indirect cesium iodide detector is much, much higher than the direct DR detector amorphous selenium version. Okay? Indirect conversion systems can save patient dose compared to direct conversion systems. They have a higher overall absorption efficiency. Okay? So, indirect systems. The phosphor layer is thicker than the amorphous selenium layer, which, remember, the phosphor layer is, those are comparable because both of those are trying to absorb the remnant X-rays. We can afford to get away with a thicker phosphor layer with the indirect system, okay, than a direct system. We can't build the amorphous selenium too thick because the electrons will reabsorb and neutralize. Oh yeah, okay, because it's not the same system as an indirect. An indirect actually uses a polarized electrode at the top to push the electrons down, or to pull the electrons up away from the capacitor. The amorphous selenium does not use a polarizing electrode, okay, and so the electrons have to drift. And if the amorphous selenium layer is too thick, they'll just reabsorb. Okay. Since light has lower energy than X-rays, Dexels, the amorphous silicon, is more efficient at photovoltaic effect than amorphous selenium is at photoelectric effect. So there's a greater probability of absorption of light than there is of X-ray. And that's with any material, because light is lower energy. Remember, what controls penetration power? Is that just for X-rays, or is that for all electromagnetic waves? Yes, that's right. That's for all electromagnetic waves. And so light photons should be really easy to absorb. And in fact, they are. Okay. So the way that we compare the efficiency of one detector to the other detector is the ratio of the signal-to-noise ratios. What? Okay. The squared output signal-to-noise ratio divided by the squared input signal-to-noise ratio. What? Okay. How are there two signal-to-noise ratios? All right, let me back up and tell you where each of those measurements is coming from. So the input signal-to-noise ratio is what we simply just call signal-to-noise ratio. Remnant beam versus scatter photons. Okay? Number of remnant beam photons divided by number of scattered photons squared. That's in the denominator of this formula. Now, the output. Number of stored charges in the capacitor over random electronic noise in the wire connecting to the amplifier. That ratio squared in the top. Okay? And then since it's expressed as a ratio of squared ratios, it can be expressed as a percentage, and that's typically what DQE is expressed as, is a percentage. Okay? So 100% DQE, that would be a perfect image receptor system. That indicates that it's capturing every single remnant beam photon. Okay? We don't have 100% DQE systems. The best we have is a 60% DQE system. That's the cesium iodide system. So no imaging system can achieve a perfect 100% DQE because we know about loss to heat too. And so if we're talking about phenomenon like photovoltaic or photoelectric effect, we know that there is entropy. And so that's why we can't have a perfect DQE, because we are going to lose some of the energy to randomness in the form of heat. Okay? Or resistance in the wire, if you like, which manifests as heat. Okay. At 70 kV, typical DQEs. Okay. Oh, look, he beats my numbers. It must have been another author that I think I got it from Buchon. 30% for CR phosphors. Direct conversion, 67%. Says 2 out of every 3 photons in the remnant beam becomes part of the image. And then indirect conversion, he actually has a higher number than me. I had direct conversions, I swear to God, Buchon said 60% for cesium iodide and only high 50s for amorphous selenium. But these numbers will work too. Will they actually ask you about the specific efficiencies? No, you just need to know that the indirect conversion system is the most efficient at 77%. Well, you don't need to know 77% because the other author said 60%. So high DQE is important because if your detector is more efficient, do you have to send more photons or less photons to capture the same quality image? The answer is less. You can get away with sending less photons because you're capturing more of them. Okay? The difference between indirect and CR is about double the number of photons are captured for any particular mass or any particular exposure. Okay? So now think of the techniques between CR and DR. Are we using about half the mass on average? And that's because the DQE is doubled for the indirect DR conversion. So if you get techniques, and those techniques are based on CR, and you're applying them to DR, cut your mass in half. That's what this is telling you. Okay? That's the practical use of understanding the difference of DQEs for the different detectors. Okay? Do you have to make an adjustment between an amorphous selenium plate and a cesium iodide plate? No, it's not a significant change. Okay? You should find a cesium iodide plate and get good DR techniques based off the cesium iodide plate, and they will work for the amorphous selenium plate. Okay? For the CR plates, you should get your cesium iodide techniques, detector techniques, and cut and double the mass, and those will work for the CR plates if you're even using those anymore. Okay. Oh, look, looks like this is the last slide. Yay! So, conversion efficiency. X-ray or light photons are absorbed. The conversion of this energy into electrical charge is nearly 100%. Okay, in either type of DR system. And so conversion efficiency into stored charges is nearly 100%. So that means it's a non-factor. Conversion efficiency in DR doesn't really factor into the overall detector efficiency because they're both 100%. Okay? So percentage of electrons that reach the capacitors, also 100%. Okay? Because amorphous selenium is kept thin. If you have a fat slab of amorphous selenium, it will self-neutralize. The electron won't drift far enough, and then it'll see the positive ion that it just left. It'll say, well, I can just land back there. That's fine. And it will do so, and then it'll self-neutralize. Okay? And you can see that in ionized gas. That's why pocket dosimeters have to be read out immediately, is because the air is ionized temporarily after an exposure, but those positive and negative ions are attracted to each other too. And so the ionized air can always ground itself out if given enough time. The electrons can pair back up with the positive ions and neutralize. Okay. In the same way, amorphous selenium, as it participates in the photoelectric effect, those electrons have to drift, right? And the positive ions have to drift, and one of those two has to be stored in the capacitor. If they don't drift because the steering forces of that bias voltage, the top electrode, is too far away. Remember what's the denominator for Coulomb's law? Oh yeah, distance. So if that bias electrode that is supposed to separate those ion pairs is too far away, well then those ion pairs self-neutralize. And I can walk you through that maybe next time if you need clarity on that. Okay? All right, so for now, we started with spatial resolution, but then we went into DQE and detector efficiency, and lots of sub-factors contribute to DQE, especially in image receptors that use phosphors. Like that there's a changing of the energy form into light. Well, then that's going to affect DQE because light does some things. We automatically lose some of the energy because light spreads in all directions. So, all right, so that's all for now. Remember, slides 1 through 46 is what I'm about to build that quiz right now, and I'm going to upload it. It's going to be on chapter 34, slides 1 through 46. And I'll have that assigned for next week. I'm also going to start building the final, and I should have that available to you probably the end of next week because we got to get the final over with early to make room for the site visit. All right, guys. Have a good weekend. I'll see you later.